Here's MDF, who is going to talk about a fixed point calculus that supports both linear and nonlinear recursive types.
Yeah, so this is joint work with Mike Misloff and Bertrand de Hovius, who are from Tulane. They're sitting over there at the back. That's in New Orleans. Okay, so linear types, nonlinear types, mixed, like what does it mean? Well, they're linear in the sense of linear logic, which was introduced by Jean-Yves Girard in 1987. And that was a pretty big deal when it was originally introduced. It has spurred a lot of research since then. There's been logicians, mathematicians, computer scientists talking about it. So the main point is that this resource-sensitive logic. So the previous speaker also mentioned it. So the main idea is that you have to restrict the weakening and the contraction rules of intuitionistic logic. And the resulting system is, well, it's called a substructural logic. And since it was first described, there's been a lot of promises about applications in programming languages and so on. So, yeah, it's been studied for 30 years at least. There's been a lot of research into it, but there are very few programming languages which make use of linear types that are actually usable. So I think with the last bullet point, I'm like pretty generous by saying that there are very few. I think most people would just say that it's zero, basically. Well, why is this the case? Well, there's probably many reasons. Well, applications, I don't think, is one of them. So here I've noted like a few applications. So let's talk about this first. Probably the most important one that people in this room might care about is concurrency. Session types, they've been used in order to introduce a typing discipline for the P calculus, and this has applications in concurrency. So session types basically make use of linear logic. Another one which I think basically nobody in this room would care about that much is quantum programming. But actually the paper was funded by a quantum programming grant, so we care. Right? So how are linear types actually used there? Well, the main idea is that quantum mechanics imposes some restrictions on quantum information. So basically, you cannot copy quantum bits, and this causes. So if you actually do it by accident, this runtime error, it's like dividing by zero. So the universe explodes. It's really bad. So you shouldn't do it. And because of this, you have to use a substructural type system, which is either linear or affine, in order to prevent this. There's also been some work in circuit description languages. So it's related to building like hardware circuits and so on. So there was a Popol paper by Robert Duran, Jennifer Pakin, and Steve Zdancevic in Popol like 2 years ago, I think. Well, we also have one paper, Lex, which talks about this kind of stuff. But also there's the traditional applications that people have been talking about for quite a long time, which is about programming with resource-sensitive data. And more recently, there was also a proposal for linear Haskell that was described in, there was a pretty good paper about it, I think last year at Popol. But I think that the proposal didn't go through, unfortunately. So anyway, so this talk, so there are applications, but I think that one of the main reasons that linear types haven't really been used that much in programming is because it's just too inconvenient to work with them. Okay, so there's like several issues. In particular, one of them is how you deal with copying and deletion of variables. Most of the people who write papers in linear logic or about linear programming languages, they usually just slap a bang in front of anything that wants to be copied, that you want to copy, and then you have to always say, I'm going to promote this, and use a dereliction and like force it and so on. So in this talk, we want to address some of these issues. We haven't been able to, unfortunately, address everything. So in particular, how can you add the recursive types without making things worse? Okay, this is I mean, things are already pretty bad. We just don't want to make it any worse. So not a very high bar, but I think we managed to at least do that. And in particular, we will show how you can actually do this while still retaining implicit weakening and contraction rules. It means you can copy and discard variables easily. And we have a very detailed categorical treatment, so I'm a new guy here at ICFP, but I noticed that so far nobody has really talked about category theory. So I'm in a bit of an awkward position here, so I'll try to minimize the categorical talk by talking about the other aspects like operational and syntactic, and the syntactic treatment. Okay, so the operational and syntactic treatment is mostly based on work that was already done. So it's been mostly described in 2 R papers, one by Francisco Rios and Peter Selinger, which is published QPL. So that's quantum physics and logic, where they talk about a quantum programming language. And well, basically, if you consider that language, there's a sub-language within it, which is mixed linear and nonlinear. And we also have a paper at LIX where we talk about similar issues as well. This is from last year. All right, so in particular, the languages that both papers talk about, they're mixed linear and nonlinear in the sense that you have both linear types, but you also have nonlinear types in order to increase convenience for programming. So in particular, the linear data, it has to be used exactly once, and this makes working with a lot of data structures like natural numbers and so on like a little inconvenient, because usually you want to use a natural number as much as you want, right? So yeah, this is one of the issues that we take care of. So in particular, if you consider recursive types like lists, like you can handle them in exactly the same way, whether you do it linearly or non-linearly. It's basically the same construct, and we show how you can interpret this denotationally as well in a very natural way. In particular, we also answer the question of how you would go about designing a linear, non-linear version of FPC. So FPC, I think, is a pretty popular type system. It was introduced by Gordon Plotkin and intensely studied by one of his PhD students at the time, Marcel Fiori. It stands for the fixed point calculus. And yeah, in this talk, we in the current paper, we describe the linear, non-linear version of this calculus. All right, so its syntax is based on mostly like pretty standard constructs, but we've made a few changes from a traditional presentation of a dual intuitionistic / linear type system. So in particular, we have type variables, which are pretty standard. You need it in order to form recursive types. We have term variables. Well, obviously you need those as well. And one of the main points here is that we consider two kinds of types. We have the usual types, and then a subset of those types are the nonlinear types. But we do not actually impose a strict separation between types and nonlinear types. So they're just a subset, okay? So in particular, the nonlinear types we consider to be unrestricted. So if you have any term which is of a nonlinear type, then you could just use it as many times as you wish, okay? So no restrictions are imposed there. Whereas a type, well, a type can be just, it could be a nonlinear one, and if you wish, you can also treat it linearly for some reason. That's okay. But in general, if it's unknown what the type is, then we would just treat it as if it were linear. Okay, so we're not going to violate anything here. So in particular, we in our type system we have the following connectors. We have plus for some types. We have pairs. We have higher order types for function space, and well, obviously we have the bank from linear logic. So this is something that we haven't eliminated in this paper. And finally, those our types are also closed under formation of recursive types. Now, the nonlinear types, they're closed under the same constructs except for function space. So function space we always treat as if it's linear. All right? Everything else, however, can be handled implicitly. So that's all right. So the type context is pretty straightforward. The term contexts are also straightforward. So in particular, the term judgments, our term judgments are a little different from what you would see in most mixed linear, nonlinear systems. In particular, we have one term judgment for the type context, but usually you're only interested in terms which are of closed type. Okay, so you could, for most situations, you can just think of the theta term as just being trivial. And now the term context is actually just one. Okay, so we do not have two term contexts, which is what most other people end up with. Most of our authors usually assume that there is a nonlinear context and there is also a linear context. Right? We just have one, and that's it. So basically, every variable in the context has a type, and whether it's a linear variable or a nonlinear variable is determined by its type. So that's it. And this actually ends up with this, it's a very simple idea, but with this you can actually eliminate a lot of the bureaucracy of having to deal with linear logic. And some of the terms that people might not be familiar here, I mean, all of them are pretty standard. It's the only ones that people might not be aware of are the lift and the force. So if you've studied linear logic, then you probably recognize this. But the main idea is that if you lift a term, so this corresponds to the rule of promotion from linear logic, and this indicates that the term actually has no free linear variables. Okay, so it means it's safe to copy it or to discard and so on. And the force is just the elimination rule of type bang. So you just get rid of the lift and you proceed as before. All right, so the operational semantics, we use a call by value big step operational semantics. Again, they're pretty standard. The only thing that people might not be familiar with is the lift and the force rules. So lift creates a thunk, so it's pretty similar to lambda abstraction in a call by value language. So it just defers the evaluation. And the force just gets rid of it, and you just continue with the evaluation of the term. Okay, so a pretty famous result in FPC is that type level recursion induces term level recursion. Right? So if you have recursive types, then you basically you get a canonical fixed point operator on terms. And well, obviously we wanted to recreate this in our language. So it's true also in LNL FPC. So I mean, this term which you see there is obviously not meant to be human readable, but if you actually do some work, write like about 2 pages of proof trees or whatever, then you just derive a recursion operator. And the recursion operator is actually the one that we had from a previous paper. So it's a pretty natural one to have. So it's all right. Okay, and let's consider a function here, so so that we can see how it looks like in our syntax. So first, this is just the formal academic syntax, right? It's we haven't implemented anything. But if we actually use some syntactic sugar, then I think this could actually end up looking a little bit better. But again, so without using any sort of syntactic sugar, we immediately see that well, because of the presence of the force, the factorial function is well, obviously worse than how you would write it in a nonlinear language, right? Because this is one of the technicalities that I was talking about that's still present. But the other things that obviously a nonlinear programmer would not even consider here is that, for example, the variable u here, which is pattern matched, is actually never used, right? And this is now done implicitly here, so we don't have to explicitly say you got discarded and so on. And in particular, the variable n, which is the natural number which is given as an input argument, it's also implicitly copied as well, because you see that you have the n here. It's pattern matched, but you also have to use it in the multiplication function. So we've implicitly created a copy. So the syntax is actually not that bad. The only thing that you have to deal with is the force and the lift. All of the other substructural rules of intuitionistic linear logic have been eliminated. And I actually think that this could be, to a large extent, fixed if you just use some syntactic sugar. In particular, if you use the standard translation of nonlinear function space as bang of A or poppy. But it can be completely fixed, but again, in many cases, it could be eliminated. All right, well, I postponed the category 3 as much as possible, but I ran out of things to say. So actually, most of the paper is about category 3. So all right, I'll very briefly say how we can interpret all of this. So we take a model of intuitionistic linear logic, also known as a linear nonlinear model, that was described by Nick Benton. So it consists of 2 categories: a Cartesian closed category on the left, symmetric monodal closed one on the right, together with a symmetric monodal adjunction in between. And this is actually used to move between the nonlinear world on the left and the linear world on the right. So that's the main idea. And because we obviously have, I mean, we're always talking about intuitionistic linear logic here, but we also have additional structure, in particular recursive types. We also have to throw in some more structure in here. And what we assume is that we have an initial object, and such that the initial morphisms are embeddings in the EP sense, in the embedding projection sense from domain theory. We assume that we have some co-limits, so we can form initial algebras. And we also have to assume that the co-products are enriched over complete partial orders. Then the adjunction is, well, it has the Cartesian category has to be the category of CPOs and Scott continuous maps. And we also assume that, as before, it's symmetric monodal. In this case, then you can prove that the category L is basically ideal for solving recursive domain equations. It's algebraically compact in the sense of Peter Freit and Marcel Fiori. All right, we have a bunch of concrete models. The simplest one is just given by pre-standard adjunction from domain theory, in particular the adjunction between complete partial orders and pointed complete partial orders with strict maps between them. And also, if you read the paper, we have a bunch of other concrete models which make use of enriched category theory. And these concrete models have been used for quantum programming and a bunch of other emerging programming paradigms. All right, so the main idea is that we have to provide an interpretation within the, we have to provide an interpretation of all of the types within the Cartesian category, which is a little complicated because usually people do it in a symmetric model, one. But we have to do this in order to describe the canonical to describe the comonoid structure of the types, so we can explain how to copy them and delete and discard them and so on. So this is actually the main issue. And the way we do it is we use the left adjoint of the adjunction in order to reflect the embeddings from the linear one into the Cartesian one. And then we have a bunch of theorems which prove that this category is actually pretty good for doing the type interpretations. So just a very brief description of the semantics. So every type is interpreted as a functor on, so every open type is interpreted as a functor on the subcategory of embeddings in the linear side. And therefore, if it's closed, it just corresponds to an object. Whereas the nonlinear types are now interpreted as functors on the subcategory of pre-embeddings. So these are essentially the reflected embeddings from the linear side. And as a corollary, we see that the nonlinear interpretation of a nonlinear type is then just an object of CPO. And then if you do, well, actually a lot of proofs, many pages, you can prove that there is an isomorphism between them, which is coherent in a very strong sense. With this isomorphism, because I'm running out of time, you can define the copy map, the discarding map, the copy map, and also promotion. And this just says that this is just a fancy way of saying you can copy and delete stuff. And the term semantics are pretty standard, not much to say there. We have soundness, we have computational adequacy, so we're pretty good. It's pretty solid categorical interpretation. All right. So basically, we have explained how you can introduce such a fixed point calculus, which has both linear and nonlinear recursive types. We thought a bit about programming convenience, which is what most people usually don't do when they talk about linear type systems. And we showed we've provided very strong evidence, like syntactic, operational, denotational, categorical evidence that this is actually a pretty solid way of getting rid of weakening and contraction. All right, and well, an open question is how to deal with lambda abstractions, right? So basically, how is it possible to actually get rid of lift of the lift and the force construction, so that you don't have to bother the programmer with this. I think that's pretty tough. There are several solutions that have been proposed based on very different results. I'm not sure what's the best way about doing this. So yeah, this is something that we would like to consider as part of future work. So thanks.
Thank you very much. I will start with a question from Slido. So ATS2 tackles this problem by making types nonlinear, but supporting views which can we tie types to linear proofs. What advantages does your approach have over it?
So what was the
ATS2. Do you want to read the question yourself?
Well, I don't know what ATS2 is, so I'm not sure if I just don't know what it is, so I don't know how to compare.
Okay. Questions from the audience? Okay.
Thanks, I'll look at it.
We have some other questions from Slido. What about co-induction? Is it straightforward to add?
Well, in this case, basically, type induction, type co-induction is the same because the fixed points just coincide.
So your model is based on L and L. This implies that in your language, the bang modality can be split into adjoint factors. Any reasons for why this wasn't done?
Oh yeah, because then you end up in a bizarre situation where you have like two kinds of term judgments. So this is actually how it was usually done by Benton and then later by Benton and Woodler. But in this setting, recursion is not very well behaved. I mean, actually, it's unclear how we would do it on the nonlinear side.
Mm-hmm.
It's less convenient, I think, for programming in general, but it could be a little subjective.
Last question from Slido. Do you have a program logic for this system?
No.
Have you used this to prove any interesting equivalences between programs? Any specific examples?
No. No, we haven't thought about program equivalences at all.
Another question from Slido. Andre Bauer asks, the simplest adjunction taking pointed domains and strict maps, does it give you a way to control totality? That is, what does linearity mean in this case?
What does linearity mean in this case? I'm not sure how to interpret the question. I mean, how does it help us deal with totality? So, I mean, there is. I don't know what to say, but this is in general. I mean, in this case, the linear category is just the Kleisli category of the lifting monad, which can be used to interpret just a standard nonlinear lambda calculus. So I'm not sure. I mean, in a sense, you could argue it's a little degenerate as far as linear nonlinear models are concerned, because technically everything has a canonical Komoloid structure. So if you want, you can copy whatever you want, and you can discard whatever you want. But yeah, you can still model it within it, which I think is to be expected.
Other questions from the audience? Okay, so let's thank our speaker once again.